This is Jack Jackson, and in this video we're going to continue our discussion and investigation into limits, an informal discussion here. And we're going to be looking at situations where we're given a graph of some functions, in some case some complicated piecewise defined functions. And we're going to see what kinds of limits we might look at, both left limits, right limits, limits as we go to infinity, just regular full limits as x goes to a particular constant. And we'll look at what kinds of situations could happen when the limit doesn't exist, or when the limit does exist, but we have some discontinuity of some kind. So remember, as we go through this, that the limit of a function as x approaches a constant c has nothing to do with what happens, if anything happens, when x actually equals c. It's dealing with what happens when x is near c. As x gets closer and closer to c, we want to find out what happens to f of x, or y, the output. Now, so let's look at a few examples. Okay, let's start with example 3 here. And suppose we're given this function here. It's defined by this graph. Now, notice that we have some holes in the graph here. Okay, we got a few straight marks here. Let's see if we can get rid of those. Okay, but this one up here is not a straight mark. That's a point on the graph. And then we have some solid points here, some places where there are no points. And this graph is made up of various different pieces. But if you notice, if you draw a vertical line, then in fact, any vertical line you draw will only touch this graph either not at all or only once. So this is in fact a function. It passes a vertical line test. Every input gives you at most one output. Okay, and so there's the function. We're going to ask some questions about several different limits. Let's see if we can get this where you can see the questions and the graph at the same time. Okay, so there's the function, and we want to be able to determine what these limits are. So in some cases they're limits, in some cases they're values of the function. So notice the difference between the two parts of question 1 here. F of 8 is talking about what is the y value, what is the f value when x is 8, what is the output when the input is 8. And so that's referring to a specific point that's on the graph if it exists. If it doesn't exist, you can write does not exist in the blank. Then this, the limit as x approaches 8 of f of x, is talking about a limit on the graph. Okay? So what I'd like you to do here is to go through here and work this yourself, and then come back to the video and check your answers. So you're going to press pause, work through it. I'll give you a chance to write down the questions. Maybe we'll zoom in a little bit more closely here. So we'll give you a chance to write the questions down. So there they are. You might pause and put those questions down, and then I'll zoom in closer to the graph for you to finish working it. So press pause now to get the questions. Okay, now you're back and you've seen the questions. You can go here, and we'll zoom in as much as I can here. And so you can see the graph. Now, go ahead and press pause again and work through this. Come back when you're done. Press pause now. Okay, so as we work through this, we should be able to come up with several of these answers. Okay, now that you're back, hopefully you've done this yourself. So the first question was f of 8. Well, f of 8, we want to see where the input is 8, which is right here. We go up, and we see the output is 4 because the point 84 is on the graph. So f of 8 equals 4. 8, the point 84 is on the graph. Now, if we pay attention to the part of the graph near x equals 8, we're looking at this part of the graph right in here, and as we approach this point here, let's just, as we approach in here, we're getting closer and closer to that point, 8, 4, which is actually on the graph. So that's the graph is continuous there. So the limit as x approaches 8 of f of x is 4, and 8, 4 is on the graph, so that is a point where we have a continuous point. Now let's look at what happens when x is 5. Now when x is 5, the point's actually up here. It actually has the point 5, 8 is actually on the graph. So f of 5 equals 8. Now we can draw a little circle around that point, and it's the only point in that circle, so we would call this an isolated point on the graph. So that's f of 5 equals 8 because 5, 8 is on the graph. Now let's look what happens as we get close to that point. As we get closer to that point where x is 5, which is this vertical line right here, okay, we see that we're coming in this way and this way on the graph from either side. We're getting closer and closer to a point right there at 5, 1. Now that point is a hole in the graph, as you can see from the picture here. That point is not actually on the graph. The point that's on the graph when x is 5 is way up here at 5, 8. But that is a hole in the graph. That's what we call a removable discontinuity, or a hole in the graph. But the limit is 1. So we would write it like this right here. The limit as x approaches 5 of f of x equals 1. Okay, so the limit exists, but the function exists, but they're not the same, so that is a discontinuity. Now, how about, let's see what happens near x equals 7. Okay, so x equals 7, if we draw a vertical line, this vertical line right here, if we go all the way up and down the graph, we see that the graph does not have a point on that line, anywhere on that line, and so f of 7 does not exist. But the limit could still exist, and in fact it does. As you see, you're getting closer and closer as you come in this way towards the graph from the right or left. It's getting closer and closer to that point 7, 3, which is a hole in the graph, or removable discontinuity. So the limit as x approaches 7 is 3. Notice that limit as x approaches 7 is 3. That has absolutely nothing to do with whether or not the function exists there. Okay, so the function might not exist, and you could still have a limit when you have a hole in the graph. The function may exist, like it did over here at 5, but it may not be the same as the limit. The limit can still exist. Whether or not the function exists at the point you're approaching, at the x value you're approaching, is totally irrelevant to whether the limit exists or not. Okay, what's the next question? Okay, we're going to look at -2. Okay, so at -2, there's actually a point right here. You can see it at -2, 1. That's an actual point on the graph, and so f of -2 equals 1. Write that this way. F of -2 equals 1, because -2, 1 is actually a point on the graph. But the limit does not exist here. As we approach from both sides, we do not approach a single number. Now we are as we are approaching from the right side. So the limit as you approach from the right side is approaching the same value, 1. And so we would say the limit as x approaches 2 from the right, -2 from the right side. So this minus right here is saying that it's a -2. This little plus right here says we're approaching from the right side. So we're taking the limit as x approaches -2 from the right side of f of x, and that is 1. Since that is the same as the limit as the actual point, we might refer to this as being right continuous. But it's not actually continuous here. We have a break in the graph, okay, which you can clearly see. Now, from the right side, we're actually approaching a point on that vertical line, x equals -2. But from the left side, there's essentially an arrow here. We're going down without bound. So as we get closer and closer to that vertical line, it doesn't actually touch it over here on this left side. It's going down, and we call this a vertical asymptote. Okay? So the limit from the left does not exist, but we can say the limit as x approaches -2 from the left of f of x is negative infinity. That doesn't mean it exists. That's just telling you how and why it does not exist. So that left limit indicates the limit doesn't exist, but this minus infinity indicates that the graph is going down forever, which is exactly, of course, what we saw in the graph, and that is a vertical asymptote. Again, this negative here says that we're approaching -2. The negative up here in the upper right says we're approaching from the left side. And so we would say the limit as x approaches -2 of f of x does not exist, because for a full limit to exist, both the left and right limits must exist, and they must be the same. So we have a discontinuity here. In fact, we've had a few other discontinuities. We have holes in the graph here and here. We can't technically draw from here to here without picking up the pencil, because we'd have to skip over these points here. Maybe draw this one in here. Here we have a discontinuity too. This is a non-removable discontinuity. We call this one here at 7 removable, because all we'd have to do is add a single point right there at 7, 3, and we would plug up the hole, and we would have a discontinuity. We would take the discontinuity away and have a continuous point. On the other hand, here at 5, we could also erase that point at 5, 8 and replace it with the point at 5, 1, and then we would have a continuous function there. But over here, it's a non-removable discontinuity, because there's no way to connect this up without erasing a big chunk of this graph and replacing infinitely many points. Okay, let's see if there's any more questions on this part. 1. Okay, as x approaches 1, then y approaches 4, and that one 4 is f of 1 is 4, so that's a point. It's a continuous point. How about 3 here? Here we have a discontinuity. The limit as x approaches 3 from the left is -4. See that? The limit as x approaches -3 from the right is +5, and then f of 3 is -4. How about at 10 here? As x approaches 10 from the left, y approaches 6. So the left limit as x approaches 10 is 6. The right limit is 4. And f of 10 is 6. So where are the discontinuities? We're talking about discontinuities, we're talking about x values. Any x values where there's a break of any kind. -2, 3, 5, 7, and 10 are the things. So we would say x is an element of that set. I think we've answered all the questions. Oh, no, there's one other question. We want to talk about limits as x goes to infinity and minus infinity. Okay, so if we're talking about x going to infinity, we're talking about as we go way off to the right side of the graph. Now, assuming that this is sort of keeping going like it looks here, it looks like it's getting closer and closer to this horizontal line, which is y equals 2. So there, y equals 2 perhaps could be a horizontal asymptote, and so we would say the limit as x goes to infinity of f of x is 2. However, if we look here on the left side and look at what's going down, that's going down forever, and so it's not leveling out, so y just keeps going down, 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 down forever, approaching negative infinity. Okay, so there is a limit on the right. Okay. Here, okay, and the limit on the right is 2, and the limit on the left is negative infinity, and that does not say that it exists. It's just telling you how and why it does not exist. And of course the one on the right we'd write as limit as x goes to infinity of f of x was 2. That limit does exist. And again, here are the x values where we had a discontinuity. Okay, so see if you can do the same thing on this one. Particularly, look at places where there are discontinuities, find the function value there if it exists, and find all the limits near those points, and do the limits as x goes to infinity and minus infinity. And specifically, here are some questions that we're going to answer on the net in just a minute. So we could look at this. F of negative 6 and the limit as x goes to negative 6. F of negative 5 and the limit as x goes to 5. The full limit and then both one-sided limits. F of 0, the limit as x goes to 0 of f of x. And then look at what happens at 5. What is f of 5 and what about the limit as you go to 5? Full limit and double-sided limits. Do they exist or not? And at 12, infinity, minus infinity. And just look at all the discontinuities there. So let's go back up here where you can see this. Let me zoom in just a bit. Okay, I think you can see that pretty well. So now what I want you to do is to work through all this on your own. Write your answers down, and we'll check them here in just a minute. Press pause now. Okay, I think I have all these things worked out. Maybe not with as much explanation in the notes. But let's look at what happens. At negative 6, which is right here, if you look at a vertical line, it doesn't touch the graph anywhere. So f of negative 6 does not exist. The function is undefined there. Negative 6 is not part of the domain. But we do have a hole in the graph there at negative 6, 4. Okay, and that's this point right here, this hole in the graph. You can see, I'll kind of circle around it. Okay, so right in there, that hole in the graph, and so the limit of as x goes to negative 6 is 4. How about at negative 5? That's another place, so there's a discontinuity at negative 6. There's also one here at negative 5. We have a break. As you come in from the left side, this approaches infinity. So we say the limit as x goes to negative 5 from the left is infinity. As we go from the right side, it's approaching, this should be an open dot here, 0, where the actual point is down here at negative 3, so f of negative 5 is negative 3. The limit from the left is infinity, which means it doesn't exist, but it goes up forever, so it means we have a vertical asymptote from the left side. From the right side, it's actually approaching a point, a specific point, the point negative 5, 0 on the x-axis there, but it's not a hole in the graph because it would have to approach that from both sides, but it's an open boundary point. And then we have this isolated point where the actual value of the function is negative 5, negative 3. Since the left and right limits don't both exist and are the same, the full limit just does not exist. Similarly, we have an open dot right here. Okay, and that one is an open dot boundary point as x approaches positive 5 from the left side, and that is 0. And as x approaches positive 5 from the right side, we're approaching negative 5. Okay, so the point 5. So we have an isolated point here when x equals 5 is y is 2, and we have left and right limits, but the left and right limits are not the same. So when the left and right limits are not the same, we have sort of a jump discontinuity. So it jumps from, say, going left to right, it jumps from 0 down to negative 5 in terms of these open dot boundary points. And, of course, actually at 5, we get a y value of negative 2. Now I also asked you back here about f of 0. F of 0 equals 5, and that's an actual point on the graph right here, a solid point, so that actually is a point where the function is continuous. F of 0 equals 5, and the limit as x goes to 0, f of x is also 5. So it's connected up right in that point, that position. The next place where we have a discontinuity right here is at when x equals 12, and we see the limit from the left is, as we come in from the left side, we're approaching this point right here, which is 12, 2, which is both a point on the graph and a boundary point from the left side. So f of 12 equals 2, and the limit as x goes to 12 from the left side is 2, right here. But if we take the limit as x goes to 12 from the right side, we're approaching this open dot boundary point at 12, 3. So the limit from the right side is 3. Now let's take our limits as we go to infinity and minus infinity. As we go to infinity, we're going to the right here, and we're approaching the x-axis, y equals 0. So we have a horizontal asymptote there, and the limit as x goes to infinity of f of x equals 0. And on the left, we have a different asymptote. As we go out this way, we're approaching this horizontal line, y equals 3. And so the limit there is 3. The discontinuities are the x values where we have breaks of some kind, and you'll see that here at negative 6, negative 5, 5, and 12. Okay, and you can list those like that. Okay, let's try another one. Here's another example of a function. See if you can answer some of the questions this time, and I'll go over these maybe a little bit more quickly in the next part here. And so here's some limits that we might want to do. Let's see, after this I asked for limits as you go to infinity and negative infinity, as well as the ones that you see here. Work this out yourself and come back and check your answers in a second or two. Press pause now. Okay, let's take a look at this. It looks like as the limit as x goes to 10 is actually 5, because there's actually a point there at 10, 5 on the graph, and the limit is 5 because it's getting closer and closer to that point, and the y value is also 5. So that limit is 5 either way. So we have a continuous point there. Negative 4 is right here. We have a discontinuity. F of negative 4 is actually that point there, so that's y of 0. As we come in from the right, we're approaching that point of 0. That would be this limit here. That's supposed to be 0. And then as we go from the left side, we're approaching this point down here, which has a y value of negative 6. These don't match, so this does not exist for the full limit. F of 0 is down here. There's an isolated point at negative 5. But the limit is actually approaching 0. When you look at negative 2, the limit from the left side is going up forever, so this is approaching infinity. Whereas you're going from the right side, it's going down forever, so we're approaching negative infinity on this side, positive infinity on this side. And I believe the function, I don't see a dot anywhere on the line, so that function does not exist. And since these are not the same, this does not exist either. Actually, these one-side limits don't exist either, but they were more specific by saying infinity or minus infinity. F of 5 is that down here an isolated point at 1. This is supposed to be an open dot right here. I'm not sure if that's very clear on the graph. And that's our boundary point, which is the full limit coming from both sides. Y is approaching 5, so that's a full limit. So both from the left and the right, the limit is 5. So the full limit exists, and that's a hole in the graph. As we go to infinity, notice that we are approaching a horizontal line here. In this case, it's not an asymptote. An asymptote is where it always stays above the graph and comes down above the horizontal line and comes down closer and closer to it, or always comes from below, getting closer and closer to it. This one is what we would call damped oscillation. It's going up and down, but less and less each time. And so it's approaching that line, even though it's going touching a line and going above and below it forever as we go out, that amount going up and down is less and less and less and less, and so the limit is still 5. We go to a negative infinity, we see that the y's are going down forever, so that is negative infinity. Okay? In the next video, we're going to look at some limits from where we start with the table, or we are given a formula and we generate a table and use the table to help us determine limits informally.